So I just want to thank everyone who's here for joining us this evening, and I know some other folks are coming in right now. So we're coming to you from Amiskatsu Waskagan, or sometimes known as Edmonton, Alberta. We're in Treaty 6 territory here, which is the traditional territory of the indigenous people, including the Cree, Blackfoot, Métis, Nakota Sioux, Iroquois, Dene, Ojibwe, Inuit, and many others. And today it's the home of many diverse peoples, and we welcome you all here tonight, virtual or otherwise. So if you're here for the first time, the Sound Studies Institute, or SSI, at the University of Alberta supports research and creative activities that centralize sound in any way. We're very open and interdisciplinary unit. We offer researchers opportunities to work collaboratively, discover new areas of convergent inquiry, and benefit from collective administrative support, as well as providing a philosophical and physical locus for sharing, exploring, and celebrating collaboration and innovation across disciplines, particularly as it has to do with sound. We're really happy to be here, and I want to just say thanks to Oliver Rossier and Tom Merklinger and Gail Mandrick, who are help me run this institute. I'm the director, Scott Smallwood. I want to note to everyone tonight that this discussion, which is part of our lecture series, we typically on the lecture series, we present the work of affiliated researchers, but also guests. And tonight we have a special guest who I'll introduce in just a moment, but I want to make sure everyone is aware that we will be recording tonight's presentation, as we always do. And we usually will, we post the video of the recording after the fact. So if you do not wish to be part of that recording, and you want to ask a question at the end, just simply don't turn on your video. And you can always ask questions via the chat if you'd prefer that. I also want to make a note that anyone who is interested in learning more about the Institute and or donating to our cause, please visit our website, Sound Studies. It's soundstudies.ualberta.ca, which is also where you can find out more about our various events that we have coming up. So about this talk, the American banjo, a fascinating 5-string instrument, very unique instrument, which is just full of timbral possibilities. It's an instrument that's a string instrument, but also I like to think of it as a percussion instrument because it's got a drum head on it, pretty much. And that membrane, that circular membrane, and the combination of that and the strings present a really, really interesting physical object that has a lot of really interesting capabilities, and it's super interesting to talk about the physics of that instrument. And so tonight, we're really, really happy to be able to present Joe Dickey, who, in addition to being an accomplished banjo player who performed for almost 20 years with Crabgrass, which is an Annapolis-based bluegrass group, and is currently playing in a group called Shenandoah Run. He is also a trained physician, or sorry, not physician, physics engineer. He has a degree from Drexel University and a PhD in physics from the Catholic University of America. He's going to be speaking to us tonight about the physics of the banjo, and I will turn it right over to him now, and just everyone welcome Joe Dickey tonight. Thank you.
Well, thank you, Scott, for that introduction. I feel like that sort of a weird career path maybe need a little explanation. One of my first mistakes in life was to go into physics for the money. That didn't work out just as I had hoped. So from there, I went into art as a wood artist. I don't have to tell you how that one ended, but when I didn't make my fortune there, I decided I'd go into music. So I'm sure that I'm going to get rich just any minute now. I would like to, a couple of things about the banjo. Let me see if I can share the screen here.
Ah, perfect. We hear banjo music.
Okay, that was, in case you didn't recognize it, the banjo. One of the nice things about playing banjo is that social distancing these days just comes sort of automatic. The banjo, as many of you know, came from Africa. We brought it over when we brought the slaves. They fabricated banjos. The one on the left, can you see the cursor on my the little arrow there on the screen? Maybe not. Okay, the one on the left is one that was actually made in Africa a couple hundred years ago, and the one on the right was one that was made here by the African Americans that were brought over. But the thing to notice about it, I think, is that it has already the fifth string. At least on this one, it has the drone string, which is still part of the American five-string banjo today. But the banjo has evolved considerably since then. It made major changes in the early 1900s and became what we now see as the sort of bluegrass banjo in about the 1920s and 30s. One thing about the banjo, well, one thing about all stringed instruments actually is a string vibrating all by itself radiates just about zero sound at all. It's just has no ability to make pressure waves in the air, so you really almost can't hear it. So all stringed instruments have some sort of sounding board. In the case of the banjo, there's a membrane that is excited by the string, which passes the vibration of the string through a bridge to this area, this surface that radiates. Harps, guitars, violins, banjos, almost all stringed instruments have some sort of sounding board, a large area part that vibrates and can radiate the sound. So another characteristic of the banjo, I would hope that this cursor, the arrow, shows up on your screen, does it? No, okay. Well, the banjo has a bridge on it that is called a floating bridge. In other words, the bridge is not attached to anything solid. It sets on the membrane, so it's much more efficient at transferring the vibration of the string to the sounding board, which is a membrane in this case. Much more efficient than, say, violins or guitars. That's why the banjo is so blooming loud, actually. Obnoxiously loud at times. Okay, well, anyway, this is how a banjo looks to a physicist or an engineer or a sound person. You have at the top a banjo, and you break that down into various systems, the systems being the string, the nut, the bridge, the membrane, and the tone ring. And then further simplifying that to two, in this case, to interacting one-dimensional systems, dynamic systems. They're dynamic systems in the sense that they support waves in the various systems, and they interact with each other. That makes some mathematical complications, but that's why we get paid the big bucks. The model that I've worked on does not include waves that go into the nut. The nut at the left end of that bottom diagram there is the nut that's on a guitar or the banjo is solidly attached to the neck. It presents a very high impedance, and there's very little wave motion that gets transferred into that. The other one on the right is at the bridge, and that has a much lower impedance, and furthermore, the energy that gets transferred into that then transfers more or less directly to the head, which vibrates, and that's system number 2 there. So that's kind of the way that we view the thing, and the model is based on that. I'm only going to have one equation. Can you see that one? You got the equation there?
Yeah, we can see that.
Okay. One equation, so I can see your eyes fogging over already, but that is the wave equation. And it almost any function of y that is a function of the x minus ct shown there will solve that equation. So that means, physically what that means is that any disturbance you put on that string will propagate unchanged in both directions, because it could also be a plus sign in here, by the way, which I neglected to put in there. If you make a simple change of variables, you get y is some function of kx minus omega t there. And the kx and the omega t are both dimensionless. So why not use, since any function of that y will solve that equation, why not use the exponential functions down on the bottom there, because they form a complete set. And if you solve it using those equations, you can use those equations to make pretty much any disturbance you want. Okay, that's all the math, folks. I'm sorry if I disappoint you on that. The next slide shows what you would do if you could generate a pulse that looked like that on a string. And it doesn't have to be a banjo, it could be a guitar or any string held between 2 points. If you could do that, and of course you can't, because anytime you try to make a thing like that, it immediately go into kind of a triangular shape. But if you could do that, then it will propagate. And it'll propagate both directions. And I'll play this movie a couple times since it's so interesting. But what happens is that the initial pulse goes in both directions, and every time it hits the end, it reverses polarity. In other words, if it starts out, well, I can't. If it starts out in a positive pulse, when it hits the impedance at the end, it flips. And so it has to, because at that point, since the differential equation is a linear one, that means that two solutions are also, or any number of solutions can add together, and they are still a solution to the equation. If at the point that it hits the wall, so to speak, either of these ends, the sum of those two have to be 0, because you're holding it tight here at both ends. So that's why the pulse after it reflects has got to be negative. What I've plotted down here is the force on the end. So if you look at the force that this string you would have to apply to this string at the end, then that's what is plotted down here. So you can see that when the pulse hits there, there and there, there and there, and so on, that's the force that's required to keep that string from flying off. It's just like a jump rope. You have a jump rope, you're wagging it in the air. You will feel the force on that rope that you have to hold in order for it to stay in your hand. And that, by the way, is the same force that would be transmitted from the vibrating string through the bridge to the membrane to cause a sound, okay? If you take a more realistic pulse, that is one that this is the picture of the pulse, or a string which you pulled up to a pluck here. And if you then use that as this pulse rather than that extremely sharp pulse and play the movie with that, you see that it does the same thing. And here again on the bottom is the force that's required to keep that from doing it. Now, the only losses in this string are the fact that when it does hit the boundary, a small amount of energy is lost into the nut or the bridge. In this case, the nut is at the right end and the bridge at the left end if you're plucking it near the bridge, which you generally do in the guitars and banjos and whatnot. Okay, so if you add to that losses in the string and what's called dispersion, which is the fact that the pulse spreads out various frequencies that are components of that at slightly different speeds, then you get something that looks more like this. And what you see going on here is, again, the forces on the bridge are plotted at the bottom, but you see that it is settling into a mode. As it progresses, it becomes more sinusoidal. That is the string, when it's first plucked, is not very harmonic. It has lots of overtones in it and lots of different frequencies. It's not a well-behaved pulse in any sense of the word, but it becomes a well-behaved pulse with time. And so when you pluck a banjo or a guitar for that matter, it sounds kind of raspy in the first few milliseconds, first tens of milliseconds, and then it settles into a note. And with a banjo, the tone of the banjo is very much dependent upon the way that this pulse settles into a harmonic pulse. So if you look at if you drive the string at a particular point, and the point I'm driving it at is the same point which you would normally pluck the string in a banjo. But if you drive it with a frequency ramp, in other words, you have a device on the string and it hums, it vibrates the string at that particular frequency, but if the frequency starts at 0 and it ramps up to a higher frequency, you can see how the string would behave for all these various frequencies. So if we do that, and I'm plotting down at the bottom here, the actual frequency of or the amplitude at that particular frequency. And you can see down here on the right, down below, the frequency shows, it goes from 0 to 1 kilohertz. But what happens, and I'll play that again because I want to talk about what happens, is that at 0 frequency, the string almost doesn't move, but there are frequencies there, and there, where the string moves a lot. So down here, it shows the frequency scale. So you can, let me see if I can do that. Okay. So what we can do is we can back the movie up now to there. The frequency is 295. That's the frequency of the first harmonic, or the first the tone of that string, the primary tone. The first overtone then would be there at about double the frequency. See, it's 590. This first one was, what did I say it was? 295 or 300, and here it's about 600, or it's exactly double. So this is the first overtone, and then the third one would be 3 times the fundamental, and that's right there. Down at the bottom right, you see 885, I think it is. That's the first, second overtone. So the string has these resonances in it that form the note for that particular string. Now the particular note of a string is determined by basically the speed of sound in the material, and that's a function of tension and density of the string. But once those are fixed, you can calculate that, and this is the calculation. So, okay. Now you can do the same thing on a membrane. And the first thing I'm going to show you on the membrane is an extremely small pulse. It's very unphysical. You cannot possibly generate a pulse like that on the string or on a membrane. But in math, we can do a lot of things that you experimentalists can't. So we like to hold it over you. And I will show you here one ray emanating from the drive point. Now this is a banjo head, obviously, a circular head. And the black line here is the place where the bridge is attached to the head. And so I want to generate a pulse at that line and watch how it propagates around the head. And and you can see it reversing polarity there. It's come back, it bounced off, it's coming negative under here. And now it's hitting the wall again, it's come positive. It'll go across, it'll become negative when it hits the other side and going across. So this is one ray of a disturbance that is put on there. And the disturbance is a damped sinusoid. The disturbance is shown here on the bottom curve. And it's a disturbance which is a sinusoidal drive, but it decays with time. So, so it starts out with a high intensity, if you will, excursion, and then it decays with time, and that's how a single pulse goes around. But now I want to show you what happens if you add a lot of these rays together. And as starting at this point and going in all directions at once. And you can see it propagating around. But again, you cannot possibly generate a pulse like that on a membrane or a string or anything else. It's strictly a mathematical exercise, but it does sort of demonstrate the complexity of the way that waves reverberate in a chamber, or in this case, a circular membrane. And you can see there's kind of a focusing effect, like right there, it kind of focuses it, and it focuses then at the source again, and then over here, it's kind of a mirror image of the source there. And that's strictly to do with the geometry. It's circular geometry. So it has two focal points, basically. And so now what would happen if you, instead of using this sharp pulse, we use a more realistic pulse and drive it at the center. The time scale here, by the way, is only about a quarter of a second, the whole entire thing, given the parameters of a banjo head, the density of the head and sound speed and the material and things like that. This whole thing would play out in about a quarter of a second. So, so if you drive with put a drive here at where the bridge would attach to the membrane, but you put, again, a sinusoidal drive of a particular frequency, or better yet, in this case, we'll use a ramp again. We'll drive at that point with a frequency ramp starting at 0 and going on to about 2 kilohertz in this case. So, and here you can see what happens, and you get a blip, there you get a blip, and there you get, so these are the frequencies at which that head is resonating. And here again, I can back this up and show you where they are. This first peak on there is it's actually clipped on the top, I'm sorry, but that is very close to the fundamental frequency of that circular head. It would be a better shape curve, a single pulse or single hump here, if I were driving in the center, but I'm not driving it on the center, I'm driving it where the bridge normally would be. So this is the fundamental frequency for the head under these conditions of tension and density and whatnot that I've chosen. Down on the right here, lower right, you see a contour plot of that. And as you get off resonance, not only does it, your contour plot looks much different here than it does, say, here. But you can see the various resonances. And the next resonance is here. That first one was at, let me back it up again to get the first one. Okay, down here on the right where it says frequency is 315 hertz. The next one is here at about 580. It is not harmonic. This is important. The resonances of a circular drum head in this case, or a banjo head or whatever, they are not harmonic. A string is. You take a string and you have the fundamental, and the first harmonic is almost exactly double that, the third one, and so on. That's not true with the circular membrane or any other shape, really. And then you can find yet another one here, whoops, there at about 840. But these are well-defined modes. And in fact, the mode number of a circular membrane is given by two numbers. The first number being the number of diagonals. In this case, they're down here on the right, you can see two diagonals that are nodes. In other words, there's very little excursion on those. You could draw those two lines up here on the main plot, and there are two lines going across at more or less right angles, where there is no movement in the membrane at that time, or at that frequency. Those are shown down on the lower right. And so the nomenclature for that mode is, the first number is the number of diagonals, the second is the number of circles, and there is only one circle there. So that mode is 2-1. If I go back to there, with one diagonal and still one circle, it is the 1-0-1 mode. That's 1-0 mode. Okay, and so on. So you can find the various modes, and you'll find that they're not harmonic. Each one though is a well-defined shape. The shape shown down here is 0 diagonals and one and 2 circles. So this is a 0-2 mode, and so on. But the important thing is that they're not harmonic. And here is a well-defined mode with you know, the 1 circle being the outside rim and 3. So this is the 3-0 mode. Okay. So, but that's the important point here, though, is that there are frequencies at which the membrane resonates. What you want to do in a banjo is you don't want the resonance of the head to be right on any note that you play, because you would get a very loud note that way. It'd be sort of a wolf tone, which people try to avoid in all instruments. So when you tune a banjo head, you want to make sure that the tension in there is such that that there is no resonance at any note that you want to be playing. Typically, you'll be close to G3 or G4. I think it's G3, but not on G3, or you'll get a wolf tone. So it's very, you have a lot of control in the banjo. It's one of the nice things about, or one of the things about a banjo that that you can make all these adjustments. You can change the mass of the bridge. You can change the tension on the head. You can change what's called the break angle, which is the angle at which the strings go across the bridge. You can make all these changes, and plus you can, I say you can fiddle with your banjo, but you can make all these changes. And part of my plan here is to see how those changes affect the tone. I'll get to that in a few minutes. But that's what the head looks like as a function of frequency. There's a nice mode there that is, and shown down here is a 1-2 mode, I think. Okay, so if you take one of those frequencies, and we'll take, say, the near 580, which was a well-defined mode here, about there. Okay, so if we take this frequency now and drive the membrane at that frequency, then you can see that it settles into that mode very quickly. Okay, we can also do it at a different frequency and see what that looks like. I think the next one is at 835, and that is very close to the other mode, the second mode of it. And then the third one I did was at 945, I think it is. No, 392. That's G4, and so what you don't want this, since this is a note that's played very often, a G4. Do people know what a G4 is? I can't really see heads nodding, except it's a particular note on the piano, if you will. But it's also a note that appears a lot in the banjo. In fact, the drone string is tuned to a G, typically. But what you don't want there to be a resonance of the head at that particular frequency. And you can see there's not. I mean, I can play that again, since you asked me to. And you can see that it's trying to find a mode, but it's just not finding it, okay? Because you don't want that wolf tone. I just do a polar plot here. It's a little confusing. I'll play it just, but you can see this, it's searching for a mode, but it's not really finding one. Now, some people have done a lot of some experimental work on the banjo and looking at these modes. So here is a speckle interferometry picture of the modes. I think these were done by Jim Ray at the Mayo Clinic. By the way, there's only a few people that I know of that have done much work on the banjo. Jim is one of them. There's a couple people down in Florida done it, and one guy was writing me quite a lot after I published my paper. The paper that started all this was the JASA, Journal of Acoustical Society of America paper, and that was God, 20 years ago. And by the way, I haven't revisited this stuff since then, so if I'm a little rusty, you'll understand it, I hope. But one guy from Caltech was talking to me, writing back and forth. He had a few things to say about, well, I think maybe why didn't you try this? And maybe I'll try that. And I was back and forth, and we had mostly agreement, but not on everything. And after a while, I got to realize this guy's pretty bright. So I looked up David Politzer, and it turns out he's a Nobel laureate in particle physics. So all of a sudden, everything he said was right. I mean, I wasn't going to argue with him, but nonetheless, he's done some of these experiments also on mode shapes of banjo heads and whatnot. And the Huber Banjo Company has hired Jim Ray to do a lot of work in making banjo rims and whatnot. So there's actually some practical application for these things. But here you can see the pictures of those modes at various frequencies. Now, these are not exactly the frequencies that I calculated because the parameters I used were different than the parameters he used, but you can certainly see the 0-1 mode, the 1-1 mode, the 2-1 mode, and he shows for some reason the 6-2 mode. We're not sure of that one, but those are real. But they're nice, cleanly defined modes because you've got a cleanly defined problem here with a circular head and strings. But if you had something else, you know, like a violin, I mean, the modes are just impossible. They're the only way to calculate these things is with a finite element. And I think they do a credible job in calculating the mode shapes of violins and guitars and whatnot using finite element. But the nice thing about the banjo is that you've got what we call canonical systems. You can solve exactly the modes and the response of the circular membranes and in strings. You really can't do that in a violin. But the violins have been, you know, there's been a lot of work on the violins. When I started this work 25 years ago, I did it on a lark because one of my colleagues said, well, Joe, you play banjo, why don't you study the banjo? I took that to mean study it analytically, not practice it. So I went to the library, and I'm not kidding you, there were 10,000 papers on violins and almost that number on guitars. There were didgeridoos, there were drum heads you'd never even heard of from Africa. There were just all kinds of it. There was not one paper on the banjo. So that's what really motivated me to write, which was something that was, you know, destined to be a seminal paper because it was the only one. But the modal structure of these instruments is very important for their tone. And, you know, they've been chasing the strads for years, trying to figure out what makes a strad a strad. But anyway, that's an aside. So one thing I did is I actually, you can get spectrum analyzers on your iPhone or your phone. And I got one on iPad, and I did a tap spectrum, what's called a tap spectrum of the head in the anechoic chamber of my living room. And if you tap it, that makes a delta function in time and in space too, but in time. So it has all frequencies in it. If you tap it, say with a little hammer or something, and take the spectrum of that, you get the red line here. And my calculation shows the black line, and I think it's truly amazing. Of course, I'm the mother of this thing, so I should. But the fact is that these calculations are fairly well rooted in experiment. So least, at least you get it phenomenologically there. I don't know what that little peak is in the calculated one all the way to the low frequency. It could very well could very well be that that's the correct one, and where I happen to tap it did not excite that, because if you do not tap it at a place where, if you tap it at a node line of a particular mode, it will not excite it. Okay, you have to, depending on where you tap it, you'll get slightly different results. So it could very well be that that I just didn't tap it in the right place to get that mode to show. Okay, so all that, what do you do with it? All the analysis done. So I decided to fabricate, if you will, some figures of merit. In other words, what is it that you really want to do in a banjo tone? It's not unusual for a banjo player to play 8 or 10 notes in a second, and it is a percussive instrument. But 8 or 10 notes, I think you do not want much sustain. When you go to the store to buy a violin, they tap it and they said, listen to that sustain, that's a note or that's a mark of a good quality. It's not in a banjo, because you don't want that. At 8 or 10 notes a second, if you have any sustain at all, it just becomes a muddled mess of sound. So you don't want much sustain. You may or may not want loudness, and you may or may not want brightness. I seem to be locked up again here. Well, I'm having trouble again getting to the next slide. Well, there it is. Okay. So here are the figures of merit. On the left are loudness, brightness, and decay. You could probably generate or gin up a couple other figures of merit, but I chose those because they are in the street talk, at least, they are those aspects of banjo tone that people talk about a lot. And so I looked at those 3 figures of merit as functions of the bridge mass, head tension, and drive position. Bridge mass is pretty simple to explain. It's just how heavy the bridge is. Head tension is simple, and it's an adjustment you can make automatically. Drive position is where the string is played. And banjo players know, as do guitar players and every other string instrument, well, not everyone, but the guitar class of instruments, lutes and things. When you pluck the string close to the bridge, you get a different tone than if you pluck it further away from the bridge. And so banjo players automatically go back and forth, as do guitar players, in where they play the string in order to get certain sounds. So I figured the drive position was a good parameter to do and to look at, and how that relates to these figures of merit. So here is the figures of one of the figure of merits. This or the figures of merit for the bridge mass. Okay, so the bridge mass in grams is listed on the bottom there. They all 3 curves coalesced at 1, because I had to take one of them as sort of a standard, and so that they're all relative to that. And you can see that as the mass increases, the decay decreases. That is, this is you want the decay to increase. In other words, the decay decreases, sustain increases is another way to look at it. But as the mass of the bridge becomes more, the decay decreases. What that means is happening is the more massive bridge, once it starts to vibrate, continues to vibrate and doesn't decay as much by passing energy on to the membrane. So that's a significant finding, I think. The brightness stays fairly constant with bridge mass until you get up to what would be about 6 grams would be a pretty heavy bridge. Anything beyond that is sort of, you never see bridges that heavy very much. So then the brightness drops off, and loudness over the range of most bridges stays about the same. By the way, that's in complete agreement with the folklore or the street talk or whatever, banjo players, they know very good and well, if you get too high a bridge, it sustains too long, and it affects the brightness and loudness in just these ways. So there was nothing new to be learned here, but it did. Okay. Now, if you look at the drive position, that is where the string is plucked. And the loudness is less if you're very near the bridge. And at some about, the total length here is half the string length. So as you're 1/4 of the way between the bridge and the nut, you get the loudest tone. And I think that's also in accordance with what people's experience is. The decay doesn't seem to change much with drive position. And I find that a little hard to explain. The brightness bounces all around the place. And I kept thinking I had that wrong, and it may yet be that I was wrong, but I just don't understand why the brightness fluctuates the way it does. I went back and redid the calculations before I published, and I kept getting the same thing. So I said, okay, it's probably right, but I really think that needs to be revisited, because I don't understand why the brightness would bubble around that way. I can see it changing. In fact, I can see it dropping considerably over the range from, say, from about 0.05 to, say, 0.2. But the amount of wiggle back up and down like that, there must be a calculation error in there somewhere. And finally, head tension, which is something all banjo players fiddle with a lot. As the head tension increases, brightness increases. That's common street knowledge. The loudness increases slightly. That's in accordance with street also. And the decay kind of wiggles around a little bit without a lot of change. So that was what the outcome of all that work was to define these figures of merit, to see what these various, the head tension, bridge mass, and whatnot, how they related to those figures of merit, or the tone of the banjo. Altogether, I think that it does sort of basically carry out, do follow the street knowledge on that, and there's no at least it provided a metric for some of these things. That's it. I'll be happy to either answer questions or make up a good story, whichever comes first. If there are there questions in the audience?
Great, thank you so much. Before we turn over to questions, I'd like to ask everyone to well, maybe first, Joe, if you can unshare your screen, and maybe if everybody could just turn their video on for a second, because I don't know, there's like, yeah, everybody has their video off. I just want everybody to wave and do a little sort of silent clap for that great presentation.
Thank you. You still have my screen on there?
Yeah, I do. Yeah, I think you just have to. Oh no, now it's gone. There,
Okay.
and now, oh, look at all those
Hello,
people.
everybody.
Yay, that was fantastic.
It looks like everybody's awake. Where did I go wrong?
So yes, I would like to invite questions from anyone. We have one in the chat here already from Mark, which is what was measured to determine "quote unquote" brightness?
Okay, I took the response as a function of frequency and put a straight line fit, sort of least squares, straight line fit to that. The slope of that line was what I call brightness. In other words, if it's level, which of course it isn't, but if it were level, the brightness would not change. or it would be one number. If it were high in the treble, then there would be a positive slope to that. If it were high in the bass, there would be a negative slope to that. That slope was what I called brightness, but it was a straight line fit to the frequency response over the 0 to about 2 kilohertz.
Great, thank you for that. Let's see, another question. Dominic has a question. Oh, actually, this is a question I had too. I was going to ask this as well. So this is a question about, you were talking about how the bridge and the bridge is in a specific position. It can weigh more. It can be made out of different materials and things.
Right.
But I was wondering, and Dominic also was wondering, how does the location of the bridge change, and is there a standard as to where that bridge needs to be physically, like from, for example, from offset from the center or whatever?
Yeah, there certainly is. To answer that part of the question first, there's a very specific place that bridge needs to be, because your frets are already on the instrument. Okay, so that means there needs to be a progression, get to an octave, and so on. If that bridge is off, the whole thing is off. So the bridge is a very specific, and that's how you set the bridge, by the way, is you, let me show you. Just happen to have a banjo here. Okay, this is, a note at the 12th fret. If you just barely hold that, you get the octave. If that bridge were not in the right place, you wouldn't get an octave, because what you're doing when you do this, I'm just barely touching the string here to get the string to vibrate in its overtone. That means that this distance from here to here and from here to here have got to be exactly the same. So there's a very specific place that bridge needs to be. Now, the other parts of the question had to do with material, or no, what was it, the first part?
No, I think you answered the question was about the location of the bridge.
Yeah.
So I think you
No,
did answer it.
There's no fudging that one. Yeah.
Yeah. Great. Stephen Lane has his hand up. This is not a chat question, so I'd like to invite Stephen Lane to, you can just unmute yourself. I think Tom will give you that ability. You can ask the question directly.
Excellent. Thank you very much for the presentation. So I'm a violin player myself, and I enjoyed that you had a little slide in there. I'm wondering about the effect. You mentioned the string affecting the bridge motion, and I'm wondering if there's any interplay back into the other strings from the bridge motion, or if you think there's any effect on the string behavior from the resonances of, I suppose, the banjo body itself.
Absolutely, there is. And this is one of the things that David Politzer was doing a lot of in order to explain what he called the twang in the banjo. And what happens when you pluck a string, of course, it stretches. And it also then would rock the bridge in addition to driving it up and down. And the connected one-dimensional systems I was talking about takes into some of that into account, but not all of it. What it does is there are waves in the membrane that are affecting the string, and the string affecting the wave. So it's a complicated interplay of these two systems. But there are things in there that are not in my model that may be important. And Politzer was quick to point that out, rightly so. The rocking of the bridge, it changes the tension in the string at a certain frequency also. And this then modulates the sound itself. And the same, very much true in the violin, that you'll get different tones, not where you bow it, but because of that rocking of the bridge. And then in the violin, you get a very complicated modal pattern, or propagation pattern in the thing itself. Now I have a question for you. Why is it there's so many banjo jokes and no violin jokes?
Couldn't tell you.
I think it's very unfair.
Agreed. Thank you for that. Colin, I'll get to you in a moment. I'm going to ask another text question first, or chat question first, which is another question that I also had as a drummer. We used to talk a lot about or debate a lot about the difference between synthetic or organic heads on drums, and whether they made a difference and how they made a difference. And so, of course, I'm wondering about the banjo. What are some of the best practices in terms of the material of the head? And maybe I'll also, Aaron Noble is also asking about the different tone rings, which is it's just a related question.
Right.
So maybe you could answer those two together.
Yeah. First, the material in the head. Of course, original banjos were made with a dead possum or something, and most modern banjos are made with mylar, and this has some big advantages because it doesn't change with humidity, whereas the skinheads did. But the tone is different. The skinheads are much mellower tone, tend to be. But the mylar heads are much louder. Of course, the bluegrass player being obnoxious, people like that, like to play loud. That's why they put us in the back. But anyway, the mylar is great because, I mean, you know, if you use a thing for a canoe paddle, which I confess I've done once, it still survives, you know. The skinhead would just go limp and things. But you can model that, and that I did in fact do that, but I didn't present that as part of the published work because there's a loss factor that has to do with the propagation of waves in the head, and skinheads, not a good term, is it? Yeah, skinheads have a lot of loss by comparison to mylar. Now there's a frosting on the mylar. They put the frosting on so that it would be a little more loss and try to make it. And you can buy mylar heads that have some material in them that cause them to sound more mellow and have things. There's all kinds of things you can buy, of course.
Great. And any comments about the tone rings?
Oh yeah, the tone ring. Yeah, excuse me for that. There's a lot of mystique about that, and there's been an awful lot of work. You know, the Stradivarius of the banjos are what's called the pre-war Gibsons, and they are really sweet sounding instruments. And people seem to think that it has to do more with the tone ring. So these tone rings have gotten more you know, that more attention than medieval bells. You know, the bronze that goes into them and all that. The work that Jim Ray did was primarily to understand why some of these really fine sounding banjos sound the way they do, and whether it is the tone ring or not. I don't think that work is really conclusive. It's suggestive, but not conclusive. And so, because there are fine banjos out there that have a wooden ring. But there's a lot of people that think that that's it. That's what makes the pre-war Gibsons the Stradivarius of the banjos.
Interesting. Okay, Colin has a question. I think Colin has his hand up, so Colin can unmute. Yep, there we go.
I like your shirt.
Yeah, I didn't even realize I was wearing a banjo.
Giveaway.
Thanks so much. This is really interesting. I have a two-part question. So I'm a clawhammer player, and I got a higher, like a bridge that's higher, just to make the technique easier as I was learning. And I noticed it increased the volume a lot. And I wondered if it also is changing the other parameters. That's sort of part one. And the second part is a lot of people who play clawhammer will stuff things in the back of the head. Old socks. I use a sponge, and all of that. And it's I think it's to reduce the decay, but I was wondering if there's anything else that you're aware of in that regard.
Well, I stuff things in there just to keep peace with the neighbors, but because it takes a lot of the volume out of it. But yeah, when you change, like if you were to change the bridge by making it higher, you're likely adding mass to it also. But then you have to to tune it, because of course that'll stretch the strings more. So you got to make sure it's still in tune, obviously. And what I showed in the one slide is what happens when the bridge weighs more. So you'll get a little bit of that effect, and it will ring for longer. That I think is, you may have experienced that, I don't know, because once that heavier bridge starts vibrating, it doesn't want to give it up. It just keeps vibrating longer.
Maybe that's what I'm perceiving as loudness. It's just that it's more.
And it does. I forget. The slide showed a slight change in loudness. But it's not.
And the stuffing of things in there, is that just to reduce the volume, or is it reducing the decay?
It just, makes peace in the family, and it can. Yeah.
Thanks.
I mean, you can stuff a lot of things in there. I mean, like articles of intimate clothing or something.
Dennis has a great practical question about tuning, which is, when I tune my banjo strings using an electronic tuner, should I mute the other strings, and does that make a difference?
I don't, but I don't think it would, actually. I don't know, because the instrument, the tuner is going to pick out the dominant tone, the dominant signal, and tune to that. The people that are like Bach and other well-known composers talked about the well-tuned clavichord or whatever it was. There's some real subtleties in that. I don't think those subtleties exist in the banjo. I really don't. In fact, there's a lot of jokes about, chainsaws are easier to tune than banjos are and things like that. So,
yeah, I can imagine that larger string instruments that have, so-called resonating strings, or even like the 12-string guitar or something, where sometimes you have strings that are similar frequencies or related to each other, really close related. That might make a difference, but
yeah. And it'll affect the tone, even if, and that's part of what Politzer was studying. The extra vibration signal waves that are generated by a moving bridge, for example, to stretching strings and things.
Jamie has a question about a fretless banjo. Just wondering if I'll just read her question, or his question. If you have a fretless banjo, my understanding is the bridge can be moved a bit to get a different tone. What would moving the bridge toward the center or the tailpiece have a similar result as changing the strike position?
Well, I think it would, actually. I don't know, but yeah, certainly if you did not have frets, then you can put the bridge pretty much anywhere you want to, because you're playing, you don't have the frets to constrain where the bridge needs to go. And you would get a different tone, there's no question about it. My guess is if you had it too close to the very center, you would get kind of a tubby sound. It'd be my guess. I haven't tried that. We could do it, but and as you get it further out toward the edge, you'll get a crisper, probably a crisper sound. But I don't know. That's something that Jamie will have to figure out, because I can't help him.
Let's see. We have a lot of questions tonight. This is great. Paul is wondering, this is sort of related to the materials question about the drum head, or the head, but questions wondering about if you could comment on the materials of the rest of the banjo, and what kinds of things make a difference.
Yeah, a lot of mystique on that too. The banjo I just showed you here is carbon fiber, and it's fine. The other one, I don't know if you can see it or not, hanging behind me, is a Resonator Bluegrass banjo, and that has maple neck. And the people will talk about the various woods that go in the neck and the various woods that go in the rim, and I think they do have a slight, excuse me, a slight change in the tone. Maple, hard maple is a crisper banjo than the walnut and so on, but I did not model that. You certainly could, and if I ever revisit this, I might. I'm not going to revisit it though, unless I have a graduate student, and I don't have any graduate students anymore. Slave labor.
Dennis also has a question
Not a very good
about.
answer to Paul on that one. So sorry.
Nope, no, I think that was a good
Well,
answer.
I mean, I don't have the answer. I know that
Yeah.
there's a lot of people that are finicky about that, and but
Dennis has a question about wondering about how to find the frequency that your head is tuned to. He says, I use a drum dial and adjust the tension to get the sound I like, but I don't know what that frequency actually is.
some people just listen. I had a lot of trouble with that myself. So I got on my iPad a spectrum analyzer, and that's been a big help. You can get many of those apps for free, and with that, I can just hit damp the strings, tap the head, and you can get a spectrum of that, and that'll show you pretty close. At least it's repeatable. There's a lot of peaks in there usually, so it's not so easy to say, well, it's tuned to such and such a note. But you can see where the primary tuning is, and then you can also see the effect of tapping it in different places. Typically you get closer to the rim, then you'll get exciting more modes, and that's why one of my previous questions, I said, if they move to the fretless banjo, move the bridge closer to the rim, you'll probably get a brighter sound. You'll probably get higher modes excited in the head. But that, to me, the use of a spectrum analyzer has been a really big help in setting the banjo so that I don't have a head resonance near or at one of my string resonances, or my note I want to play. You'll get a wolf tone. That's noticeable.
Okay, I think we have managed to get to the end of all the questions. So, and probably right on time, because we're a little bit after 8 o'clock. So maybe I will take this as an opportunity to just have us give one more round of applause to Joe tonight for this wonderful talk.
I would say throw money, but it may not work.
Great. And thanks everyone again for coming this evening. It's been wonderful to see you all.
I can't tell you how much I've enjoyed giving this talk from sunny Maryland.
And I want to thank you, Joe, for the work you've done, because as you said, not a lot of work has been done on the physics of this instrument. And you and I talked earlier before we spoke. I was talking about the steel pan, the Trinidadian steel drum, which is another instrument that has had very little work done. And this work is really important. So just thanks for the contributions that you've made. It's really fantastic.
Okay.
Thank you. Thank you.
All right. Well, we'll see everybody next time. We're going to have another lecture coming up on February 10th, 7 p.m. Wednesday. Christine Gupta will be joining us to talk about musicians' health. So stay tuned for that. And thanks everyone for your time. Have a safe evening. Stay warm. And we'll see you next time. Thanks, everybody.